We're looking at two triangles that we know are similar based on the angle-angle similarity postulate. We've got two pairs of corresponding angles that are congruent. We've got the 29-degree angles that we know are congruent to each other, and the right angles congruence theorem lets us know that this pair of right angles are congruent to each other as well. So again, we're working with similar triangles, and because the triangles are similar, we know we have proportionality between the side lengths. We can use that proportionality to help us write the following proportion. We know that the opposite side will be to the adjacent side in the triangle to the left, and then we just follow that same pattern in the triangle to the right. So the opposite side is to the adjacent side as x is to 5. So now we've got a proportion, which is also an equation, and if we only knew what the value of the opposite and the adjacent were, we could then solve for x because we'd only have one variable. So here in Sketchpad we've got another triangle with a 29-degree angle and a right angle, and we have the opposite side length measured, and we also have the adjacent side length measured, and it doesn't really matter how big or small the triangle is. All these triangles, every time I stop, we've got a triangle that is similar to the other triangles. So let's use the number calculate feature to determine the ratio of the side opposite to the side adjacent. So we'll take the opposite and divide it by the adjacent, and we get a value of 0.55. Let's go ahead and take that to 4 places to the 10,000ths place, and we get 0.5543. Now notice, even if I change the size of the triangle, that ratio stays the same because that's true for all right triangles with an acute angle measuring 29 degrees. So we know that the value of the opposite over the adjacent is 0.5543. So as I was saying, in this picture, we've got three variables. We've got the opposite, we've got the adjacent, and we've got x. If we only knew the value of the opposite and the adjacent, we could then solve for x. Well, we can actually bypass knowing the value of the opposite and the adjacent because we actually know the value of the opposite over adjacent. In Sketchpad, we showed that for any 29-degree right triangle, the opposite over the adjacent was 0.5543. So we could take the opposite over the adjacent away and replace it with 0.5543. And then it's pretty simple from here. We're going to change 0.5543 to a fraction by making it 0.5543 over 1. So then we cross multiply and we get x times 1 equals 0.5543 times 5, and when we perform that multiplication we get a value of approximately 2.8 centimeters for x. So let's take a look at another example. This corresponds to section 8 of the packet that you're working on. We again have a pair of similar triangles. We know they're similar by the angle-angle similarity postulate, and the fact that they're similar means we have proportionality between the side lengths, so we're going to be able to go ahead and write a proportion that looks like the opposite over the adjacent in the first triangle. Opposite over the adjacent is going to be equivalent to 8 over y in the second triangle, the 8 being the opposite in this triangle and y being the adjacent. And again, if we only knew the value for the opposite over the adjacent, we could just swap that out and substitute it in. Well, it just so happens that we do know the value for the opposite over the adjacent. Now remember, for any right triangle with a measure of 29 degrees, we have the value of the opposite over adjacent as 0.5543. So let's go ahead and swap out the opposite and the adjacent with 0.5543 because they're equivalent. And let's go ahead and turn 0.5543 into a fraction. 0.5543 over 1, it'll make it easier for us to cross multiply. And when we do cross multiply, we get a value of 0.5543 times y equals 8. Then we can go ahead and divide both sides by 0.5543, which will leave us with a value of 14.4 centimeters for y.